to the blue room. We started on Thursday with a talk which discussed Andrew Strominger's work. We've got the man himself today. So, without further ado, recent developments in flat space holography.
Thank you. So, it's a pleasure to be here, and I'm going to talk about some approaches to quantum gravity today. So, in our first lecture from Juan, we heard about trying to describe gravity, or quantum gravity, in anti-de Sitter space by defining it in terms of a quantum field theory without gravity that lived on the boundary. And then we heard from Renata about an approach to quantum gravity in which one used only, I think it was mostly flat space, using only diffeomorphism invariant variables. And then we also just heard from Ted about trying to understand quantum gravity in flat space without boundaries in causal patches. Now, what all this proves is that we don't know how to describe quantum gravity. It's still up in the air how we ultimately should think about it, and there are many different approaches. And here, what I'm going to talk about here sort of takes pieces from these different approaches, and I am going to be talking about flat space, not de Sitter space or anti-de Sitter space. And I am going to be trying to describe it in terms of a theory which lives on a boundary, but it's not quite what you would usually think of as the boundary of Minkowski space. And also, I'm not going to try to describe it in a fully diffeomorphism invariant way. In fact, the central piece of my approach is that there are very important diffeomorphisms, the ones we're most familiar with being translations and rotations and so on, which act non-trivially and go a very long way, and these need to not be eliminated but kept, and we're trying to understand how far they actually go in defining the theory. And so the basic idea is the basic idea is in an asymptotically flat space, certainly a quantum field theorist or a quantum field theorist doing gravity would try to describe the theory in terms of an S matrix in which you have incoming particles coming from past null infinity, interacting in some complicated way, and then going out to future null infinity. And really the starting point for this is, actually this was something that was noticed already by Dirac, is that you can think of this, now this is a tautology that you can do things this way. You can think of this, we can label, here we just have null particles which go out to null infinity. Something similar can be done for, more subtle, but similar can be done for massive particles. Here we have outgoing particles at various points on the sphere, representing the angles where they go out, and incoming particles at other points on the sphere. In addition, each one of these insertions is labeled by ordinarily, the energy, charge, or whatever other quantum numbers the particles happen to have. Now, it's a tautology that you can do this, which is writing the S matrix in different variables. But a nice thing that happens is that the Lorentz group, which is SL2C, acts as the global conformal group on this two-dimensional Euclidean sphere. So this sphere has a name, it's called the celestial sphere. And so we know that this object, the S matrix, has some of the properties of the correlators in a two-dimensional conformal field theory. Now, the thing that has happened sort of gradually over the last 15 years, and particularly over the last 4 years or so, is the following. We know many examples in condensed matter systems where once you have global, so this is the global conform, SL2C is the global conformal group in two space-time, two Euclidean space-time dimensions. Once you have that global conformal group, as often happens when you approach a fixed point in some kind of condensed matter system, there's often an enhancement to an infinite dimensional, the so-called local conformal group. And what's been realized is that this actually happens in quantum gravity. And this was first conjectured really on the basis of analogy with things in anti-de Sitter space, and then it was work by Barnick and Grant and others who talked about super-ray rotations, and then it was proven at the level of Feynman diagrams by Cachaso and myself by the discovery and proof of the so-called soft theorem. So soft theorems are relations among Feynman diagrams that tell you about the behavior of those diagrams when one of the external particles becomes soft. So, and I think I won't be explaining how that goes. That's several years old now. But let me just say that first there was the BMS group that was discovered in the 60s. And some time ago we showed that that BMS group was just identical to something that had been discovered by Weinberg called the soft graviton theorem. And that told you the leading order behavior of a scattering amplitude when one of the external legs becomes soft. And there are also subleading soft theorems, which there's been a great industry in quantum field theory of understanding their renormalization properties and so on, going back now for, I think, 60 years. So these are understood in a very rigorous and complete way. And we discovered a new subleading soft theorem. It was an analog of Lowe's soft dipole theorem in QED, which was discovered in the late 50s. And it was discovered in gravity, and it has the consequence that this global conformal group acting on the sphere here actually gets enhanced to a local conformal group. So now we've learned that if we rewrite the S matrix in this way, it has really a lot of the properties of two-dimensional conformal field theory. And this is an exciting thing because of practically of all the systems in mathematical physics, two-dimensional conformal field theories are the ones that we have the most tools to analyze and constrain their properties and so on. Now, these conformal field theories differ in, they aren't unitary discrete systems like, the 2D Ising model or some that we're more familiar with, but nevertheless, there's a lot of power in this local conformal symmetry. Okay, so why is this an interesting thing to do? Well, one is, it's just a new way of looking at quantum gravity and quantum field theory, and as we'll see, things that were patently obvious in the old way of looking at them are obscure in the new way, and things that were obscure in the old way become obvious in the new way. So finally, secondly, one would like to generalize the notion of holography beyond the amazing but incomplete story where you have quantum gravity in a bulk anti-de Sitter space is dual to some kind of conformal field theory which lives on the time-like boundary of that space. Here we're proposing something specifically that there may be some sense in which quantum gravity in asymptotically four-dimensional Minkowskian space-time has an alternate dual description in terms of some kind of conformal field theory that lives on the sphere. Now, the approach in the philosophy here is very different than in ADS-CFT. In an ADS-CFT, the ADS-CFT correspondence was, well, it had an early phase due to Bronner and Hanot, which is more like what we're doing now, but sort of the modern part of it. It was discovered, it assumed the whole apparatus of string theory, and it was shown that you had certain kinds of quantum systems that in one limit looked like a bulk theory of gravity, and another limit looked like something that was on the boundary. But in other words, the whole machinery of string theory was assumed. Here we're not assuming anything. We're just using the properties and the symmetries of the Einstein equation and organizing them in a way that is different than is what usually done. And we don't know what the conformal field theory is. We're trying to find out what the conformal field theory could be, and we're just trying to deduce that from the Einstein equation and the matter equation. Now, one of the reasons that this is interesting to me is that the discovery, so in the last number of years, there's been discovery of these new symmetries in asymptotically flat general relativity. They should affect, and I think maybe Malcolm talked something about this, there's new conservation laws. Black holes are not free to evaporate willy-nilly. They're subject to, like everything, to the conservation laws. This should have some effect on the information. But a much simpler problem than how black hole information formation and evaporation is constrained is what are the basic constraints on the S matrix. In fact, we can ask a very simple question, and we'll get some distance to the answer to that today. What is the most general form? We don't know the answer to the question. What is the most general form of four graviton scattering that's consistent with everything that we know about general relativity, unitarity, and so on? And many people in the literature have come up with different unitarity, causality, different ways in which this is constrained. Here we're talking about how it's constrained by these symmetries, and so that's a precursor to this more difficult problem. Another thing is, as we're going to see, it gives us a new way of looking at the relationship between the infrared, new and surprising way of looking at the relationship between the infrared and the ultraviolet. I'll come back to that. And finally, it's just a new way of setting things up, and we're running into some weird and surprising and enticing things. So, my starting point here is, this is kind of the earliest version of this story came from De Boer and Solidukin back in around 2001. And what they did is they just noted that let's take, and they didn't really claim to have shown very much, they were just making a conjecture, which turned out to be true, but, and they said, let's take Minkowski space, Graviton Minkowski space, and let's slice it into hyperbolic slices. And each one of these slices up here is a Euclidean ADS3. Here we have a three-dimensional de Sitter slices, and down here we have another set of Euclidean ADS3 slices. Now, and here's the metric, this is the flat space metric, where it's all multiplied by, here we're in the future quadrant, this is like a Milne universe, and here it's multiplied by a constant which is growing as we go up this way, times a unit hyperbolic slice. And what these people said is, okay, well, the hyperbolic slice, we analyze the diffeomorphism, there's boundary terms, we do the algebra. This looks just like Brown and Hainaut, and we know from Brown and Hainaut, whenever you get ADS3, you get some conformal group on the boundary. This wasn't meant to be rigorous, but they conjectured that, and then you can write down the generators of the conformal transformations, which are generated by vector fields on this conformal sphere. So the celestial sphere. The celestial sphere is the sphere that lives at this boundary here. And they said, okay, we should have some sort of a copy of the conformal group here and a copy of the conformal group down here. Now, what we showed much later, so then after this, importantly, Barnick and Troussart did a more careful analysis of the original BMS group, and they argued that the BMS group, which is angle-dependent translations along scry, should actually be enlarged to include this larger group. That the treatment of the singularities given by BMS was too stringent and should include this larger group. But both of these were not quite rigorous enough. But then Cachazo and I showed that if you just look at the S matrix for gravity coupled to matter on this background, you find you can prove using the same sort of classic quantum field theory techniques that are used to prove solve theorems, that there's a subleading solve theorem that, in fact, is the word identity of a symmetry. It can be used to reverse engineer and conclude that there is a symmetry, and that symmetry is precisely the predicted conformal transformations acting on these hyperbolic slices, with one very interesting twist. And the conservation law associated with these symmetries relates past and future null infinity and ties together the conformal transformations on the past celestial sphere with the future celestial sphere. So from this drawing, you would think there would be two spheres, and the S matrix would be a map from one to the other. But in fact, there's only one sphere. Their conformal structure is tied together, and there's only one symmetry that, that moves the whole thing at once. Now, for those of you who are familiar with with ABS, this subleading component of the energy of the metric, subleading component of the metric on the hyperbolic space is known as the Performin stress tensor, and it varies under these super rotations. And so we used the Wold formula, which Ted was talking about in the last talk, to construct the generators of these super rotations. And, okay, the formula gets a little complicated, that's it. But the upshot is that the Wold formula can be written, the generator of super rotations is the symplectic product over these hyperbolic slices of the linearized metric fluctuation with the superrotation variation of the three-dimensional Performin stress tensor. So what I'm saying is that there is a rather direct and simple uplift between the quantities in ADS3 and the quantities in four-dimensional Minkowski space. And the hope here is that the thousands of papers written on ADS and constructing the symmetries in ADS that this is going to give us a dictionary which enables us to apply all the progress in ADS to flat Minkowski space. Yeah, so then we have these charges, and because of the way it's written, we really have three pieces. We have the sum over the charge over the future hyperbola, the sum over the past hyperbolic slice, and then the sum over the DS3 slices. Those have to sum up to 0. And the statement that those sum up to 0 is equivalent to the subleading soft graviton theorem. And moreover, one can show that this particular charge for yz equals 1 over w minus c is the stress tensor which generates conformal transformations on the two-dimensional sphere. So just to say that again more simply, you can take the fields on four-dimensional Minkowski space, and there's a linear combination of them that has the property that if you go back up here, there's an operator that you can, that was an explicit if lengthy formula for it, an operator which you can insert on this celestial sphere up here. We can rewrite the S matrix this way. And it obeys all the Ward identities of a two-dimensional stress tensor in a two-dimensional conformal field theory. So there's a really very precise relationship between, completely precise relationship between two-dimensional conformal field theory and quantum gravity on four-dimensional Minkowski space. And so we want to use some of the many constraints that we know about in two-dimensional conformal field theory to constrain the properties of gravitational scattering in four-dimensional Minkowski space, to constrain the black hole S matrix, constrain the four-point function of the graviton. Okay, so some things are different, some things are the same. So in the kind of holography that Juan was talking about, there's a bulk theory which has one time and d space-time dimensions, and a boundary theory, which is a quantum field theory without gravity, which has 1 time in d minus 1, or in some cases d minus more, fewer d, but always the same number of time dimensions. Here it's different. This conformal field theory that lives on the boundary, on the celestial sphere, is Euclidean. And its correlation functions compute the S matrix of the 4-dimensional theory. The conformal field theory is also rather different. It's a different stripe, a different kind of conformal field theory, which I'm about to talk about. So let me go on. What kinds of properties does this conformal field theory have? So again, this conformal field theory is not something that we're positing or we're pulling out of string theory. We get the conformal field theory by rewriting the gluons, gravitons, whatever particle you have in 4-dimensional Minkowski space, by rewriting them according to this algorithmic dictionary that enables you to take anything in flat Minkowski space and rewrite it as a quantity on the 2-dimensional sphere. So what's the same? This is a usual garden variety conformal field theory. And what happens in these celestial conformal field theories? Well, they both have 2 Versaro algebras that generate the conformal group. They both have current algebras. So current algebra is a conserved current in the conformal field theory. The soft photon theorem, for example, gives you a current algebra over here, which is a standard U1 current algebra, which is much studied in ordinary conformal field theory. In ordinary conformal field theory, you talk about singularities in the operator product expansion. What happens when 2 operators come near each other on the sphere? That's also a subject of great study in 4-dimensional Minkowski space. It's a different name. You talk about collinear singularities. When you, for example, have 2 jets which come near each other, what is the structure of that? One of the biggest differences is the kind of representations. So in the ordinary conformal field theory, you have what's called highest weight representations, and these have are labeled by discrete integers. Here you tend to have continuous, it was shown that a complete set of plane wave states for either graviton, for any spin actually, is given by operators which are in a continuous unitary principal series. There's locality in usual conformal field theory. We don't know what the analog of that is here. Here we have the statement that the 4-dimensional S matrix is unitary. We don't understand yet what the translation of that statement is to 2 dimensions. It may be some kind of completeness statement that if you put a complete set of operators, insert them in the sphere, you get the sphere back. There's crossing symmetry in ordinary conformal field theory. We don't know what that is here. And the most surprising thing, which is what I'm going to talk about, is that, so 2-dimensional conformal field theories, the reason we have so much control over them is that there's an infinite number of symmetries, the conformal symmetries. And this greatly constrains what kind of behavior the correlation functions can have. These theories, in addition to having the conformal symmetry, which, as I said, is equivalent to the subleading soft theorem, they have an infinite number of other symmetries. One of these is space-time translation invariance, or super translation invariance. So if we go back up here, translation invariance does something simple here in this picture, but here it does something very confusing. And in fact, there's super translation invariance, which tells you in quantum gravity there's super translation invariance, the BMS invariance, which tells you that you can translate every point on the celestial sphere at null infinity separately. And that does something really strange over here. And all the correlation functions must be well behaved under that. And that gives us a huge number of constraints, and we'll see that it comes very close to determining what the correlation functions are. And finally, usual conformal field theories are an old beast. They've been analyzed for the last 30, 40 years, and these are a new kind of animal, and there's a lot to understand about them. So over the last year or two, there's been a lot of work on this from different points of view. We don't fully have the organizing principle. I can't tell you what the conformal field theory is that gives gravity or that gives Yang-Mills theory, but there's a lot of really interesting structures which I'm going to tell you about, which are popping out. Okay, so one of the basic results in this subject, I'm going to talk mostly about massless particles. For massive particles, there are also some very nice results, but they just take a little longer to state. And so let's suppose we have an ordinary scattering amplitude in momentum space for massless particles. I'm really thinking about photons or gluons here, labeled by the momentum P1, Pn. Now, for every P1, Pn, you can make a Z by taking this ratio, and that gives you a point on the celestial sphere. This Z is the point to which the momentum is headed. Okay? And that's not all the information in the gluon. There's also its energy, omega. So it turns out that if you take a Mellin transform, that is, these H's are arbitrary, you can get amplitudes, the Mellin transform amplitudes, and these have the property that they transform in a simple way under the conformal group. They transform like highest weight states with conformal weights. So what are the conformal weights of something? If you have something which is so here we have a momentum P. It goes towards a point Z in the sphere, and then we have a boost, let me call it B, which heads towards that point. And then we have a rotation R. Then we have an L0 eigenvalue, which is B plus IR. It's kind of like what they used to call twist, except I don't think they put the I in twist. So you characterize things according to these eigenstates. That's what works out to be something simple under the conformal group. Those are what we would call L0 and L0 bar, and that would be this H and H bar up here. That would be H and H bar up here, and that's these H and H bars. So you can vary this continuously, and so you get a continuum of operators in this conformal field, labeled by their boost weight and their spin, and the point at which they're inserted in the sphere here. So this is a transformation of the scattering amplitude of a four-dimensional field theory into a kind of correlation function in the two-dimensional conformal field theory. And when you write it this way, the fact that it transforms properly under the conformal group, the two-dimensional conformal group, is completely manifest. And so you can start using properties from the yellow textbook on conformal field theory. Now, so one thing that's already a little strange here, we know, so Bistersky and Shao showed that a complete basis of normalizable plane wave states are obtained if we take this conformal weight lambda to be 1 plus I times an imaginary number. This lambda this lambda is real. And so that means we actually know all the operators in the conformal field theory. So if you look at studies of conformal field theory, finding all the operators is a hard part, right? But here we know completely the spectrum of operators by construction from the field theory. So these lambdas have been computed in a lot of examples. One of the interesting things, these amplitudes, is that if you try to compute them, recall we had to do this integral over the energy. And there's no guarantee that that will converge. And indeed, if the interactions are not soft and ultraviolet, it won't converge. It's marginally convergent for Young-Mills theory. It doesn't work in Einstein gravity. It does work, it's been done for Stieberger and Taylor in string theory. And indeed, you probably want to define the Yang-Mills amplitudes because of these divergences you don't know how to deal with by embedding it in something like string theory and then taking the alpha prime goes to zero limit. So it's interesting that there are ultraviolet divergences already at tree level, and which leads me to the conjecture, which the main motivation for is I don't know of any counterexamples, I have strong evidence for it, but that a quantum perturbation expansion of a classical field theory exists if and only if the conformal basis amplitudes exist. So that would rule out gravity, but not string. That would rule out Einstein gravity, but not string gravity. So there have been a lot of interesting connections with fundamental string theory that have come out. Just by dimensional analysis, these lambdas are dimensionless. The amplitudes can't directly involve the string constant alpha prime because it's dimensionful. It only appears as a power in front, and what happens is that stringy effects appear in the soft expansion about the Reggie limit. And another interesting thing that happens, there's another tantalizing connection here. We, of course, know another theory in which the S matrix is given by a conformal field theory on the sphere. That's string theory. That's the string world sheet. And so there should be some kind of, so that it's interesting that we've just used general relativity, but there's stringy features coming out. We're seeing something where the S matrix, at least in some approximation, the approximation being when these lambdas go to infinity, is pinned to the string world sheet, becomes the same thing as the celestial sphere. Okay, now in quantum field theory we have soft theorems, which tell us what happens, very special things. So these soft theorems that we've discovered in the last 5 years are asymptotic symmetries. The asymptotic symmetries that are familiar to general relativists have also been known to quantum field theorists. They just called them soft theorems, and they wrote them in a very different language. Now, a soft theorem is a statement about what happens when the energy of a particle gets very low. And, of course, by the uncertainty principle, the energy getting low is like going out to infinity. That's why it's like an asymptotic symmetry. Now, we can't have soft theorems here because we don't have energy anymore. We've done this Mellon transform. We only have this boost weight. Nevertheless, you get something which is morally equivalent. You get conformally soft theorems. And various groups in the last few months have proven a variety of conformally soft theorems. But it's a little bit surprising that they're true, because the effective field theory description for soft theorems that one uses to derive the soft theorems can't be used here because these amplitudes and Mellon bases probe arbitrarily high energies. Now let's look at the super translations in gravity, and that's where something very interesting happens. So the super translation in gravity, we have an operator for which the boost weights, that is this B plus IR, and the B minus IR, it has spin 2, so these, they're not complex conjugates of one another. I'm in trouble with this. Okay, this thing and this thing, if we take lambda to 0, so for generic lambda, this would be an ordinary propagating graviton, but something special happens when this lambda goes to 0, and we have exactly these conformal weights. One can show, and it is the Weinberg, this is Weinberg's soft graviton theorem that I've written here in rather different notation. It's also the BMS symmetry rather in different notation. It says that there's a soft graviton operator with the property that if you take it near any other operator, you get a collinear pole. That's this 1 over z minus w. And at the same time, you shift the conformal dimension of that operator upward by 1/2. Now, this is a very, very strange thing in ordinary conformal field theories. You don't see identities like this. And indeed, in ordinary conformal field theories, the operator dimensions don't come in continuous families. So such a relation wouldn't even be meaningful. So we have some set of, so this isn't the only such symmetry that does this odd kind of thing. But what we've shown is that if you take, now I want to write down an operator product expansion. And this is some work that's true here. So let's imagine we take two operators, positive felicity gluons, and we let them approach each other on the celestial sphere. And we give them arbitrary conformal weights, boost plus translation weights, H1 and H2, and we let them get near each other. Well, just general conformal invariance, just general symmetries that are obvious. We have to match the dimensions and so on. This is basically the only thing you can have on the right-hand side, where this B here is an arbitrary function that can depend on these conformal weights in an arbitrary way. So this B is the physical data that's how many I have left, or how much I'm over?
You've got 10 minutes left including the session.
Okay. So this B here is, now you can compute this B using Feynman diagrams. So people have computed collinear singularities in Feynman diagrams. And you could compute the B by going to Feynman diagrams and then doing the Nolan transform. However, just taking this identity I had on the previous page, and I could do a contour integral with respect to Z, and I would get something where I would shift O by half and half. Using that identity, I get a recursion relation for B, that B has to be, B of H1, H2 has to equal to the sum of the B's with H1 and H2 respectively shifted by a half. Now there's another symmetry. There's a plethora of these asymptotic symmetries, and they have a very intricate self-consistency structure. So there's another one, the so-called subleading soft symmetry, which was discovered by Francis Lowe in 1957, that governs the subleading piece in the soft expansion. And it has a certain, and he didn't write it in this way, but we've just rewritten it. And it gives a second recursion relation between these B's. So now we have two recursion relations between these B's. And in fact, these two recursion relations, together with a boundary condition at asymptotically large h, that it not blow up, uniquely determines the B to be the beta Euler function. So we never had to do a calculation. We just used the symmetries to compute the operator product expansion. And this also works for the case of two positive Felicity gravitons, positive graviton, positive gluon, and we're working on the mixed Felicity case, and there's some chance that it works there. So this demonstrates that these symmetries are extremely powerful. That they give us it's very hard to. When you first look at it, it looks like too many symmetries. It looks like there shouldn't be any solution. And in fact, you barely get one. And so here we've constrained, we're constraining the 3-point OPEs. We want to go on from that eventually to constrain scattering amplitudes, and ultimately to say something about black hole evaporation. So let me just list some open questions here. Can we get all the gauge gravity OPEs to be determined from these asymptotic symmetries? And there's also something that it almost looks like we've done too much here, because in conformal field theory, in the yellow book, the textbook for conformal field theories, it says that if you know the spectrum and the OPEs, that completely fixes the spectrum and the 3-point OPEs. Conformal invariance then completely fixes every aspect of the entire theory. In other words, that's all the data there is in the theory. Now, those conformal field theories, of course, obey things that our conformal field theories don't. They have discrete spectrum, they have different kind of unitarity, they have, so it doesn't automatically apply here, but it is true that, it certainly is true that having the full spectrum in the OPE is an awful lot, and so we'd like to understand to what extent does that give the full CFT. And it's also very surprising. Saying that it gives the full CFT would say that it gives the full quantum theory of gravity, right? Because we've recast the quantum theory of gravity as a theory in Minkowski space. Now, it would be surprising. You might think that you could have a quantum theory of gravity. Okay, so this is a vague comment here. But you might think that you could have two quantum theories of gravity that differ only by, the Wilsonian point of view on physics or on quantum gravity is that you can have lots of stuff in the ultraviolet, lots of different theories in the ultraviolet that differ only by some unstable massive particle that you can integrate out. You can have many different theories in the ultraviolet, all of which give you the same thing in the infrared. But here it almost seems as if there's the possibility that by looking in the infrared, and by infrared I mean in the celestial sense, that by looking in the infrared, that you can determine the full spectrum. And so it suggests that quantum theories of gravity are much more tied, that the infrared and the ultraviolet may be much more tied together than we might have thought, and that that there isn't so much ambiguity about what goes on up there. And I guess I mentioned this before, there's been a lot of discussion in different groups using different kinds of arguments that are constraining possible 4-point amplitudes for the graviton, and it really seems to be getting chased into a corner, and so it will be very interesting to see. This strikes me as something that might be doable in the coming future, is to write down some sort of general formula for graviton scattering that is the most general thing, consistent with some assumed particle content and with all the various symmetries that we'd like to hold. So in conclusion, the reformulation of quantum gravity and Minkowski-4 as correlators on the celestial sphere is leading to novel insights, and we have a lot to understand about it.
Okay, let's have 5 minutes of discussion because we've got a lot on our schedule this afternoon. First question.
Thank you. In string theory, it's often said that there are no continuous global symmetries in quantum gravity. Is there something that you can say about it within this framework?
I think that if you had a theory with a continuous global symmetry, so really what I was talking about, if there were more stable particles, so these OPEs are defined out at infinity. So the only thing they care about is stable particles. They could also be massive, but massive or massless particles made out to infinity. I think that if you posited stable particles that had continuous global symmetries, that the program of determining the OPE from some principle would be doomed to failure. I think it's problematic. It doesn't look nice in this way of looking at things.
Thank you.
There would be none of these symmetries would determine how the OPE depended on the global symmetry.
Any more questions? Yes.
Let's go there.
Okay. More efficient.
I did not really understand your strong speculation about this ultraviolet infrared connection. let's take two theories. One is pure gravity, and the other one is gravity coupled to massive electrons. So the infrared scattering for gravitons is perfectly the same. The spectrum is definitely different.
It was important to say, I may well have misspoke. Two theories with the same stable spectrum. So,
Take stable electrons, it's fine. Conserve
but-
charge.
well, but
Massive, integrate them out. Same infrared.
no, but they're stable, so they make it to infinity.
Also, you said unstable. I just didn't get your statement.
I'm sorry. That there can't be two theories that differ only by an unstable massive particle. So and it's important that you don't, in gravity coupled to electrons, you need to include electrons to have a unitary S matrix. But when you have an unstable massive particle that never makes it out to infinity, you have a unitary S matrix without the particle because the particle is never present in an asymptotic state. And just to say again what the motivation for that is there seems to be some admittedly very vague picture here that some sort of low energy data, if we follow what's true in ordinary conformal field theory, that the spectrum and the OPEs determine the full theory. Here, if we imagine that, again, that the spectrum and the OPEs on the celestial sphere determine the full theory, which of course is a big if because these kind of conformal field theories are not, we don't understand how they're controlled, but it suggests that this data should determine the full theory, and that cannot be the case if there are two theories that lead to the same stable spectrum and OPEs and are both ultraviolet consistent.
I mean, usually, in statistical systems that have conformal symmetry, you can of course start in the ultraviolet from very different systems. They all flow to the same fixed point. Then of course exactly on the fixed point you can extrapolate back. But you never know really where they came from in the flow. Why should it be different for gravity? So all observations from functional renormalization, I know they just behave as other theories. There's a flow towards relative fixed points and you cannot go back.
Well, because the gravity is the theory at the fixed point. The gravity theory is conformally invariant. It could be possible that it certainly almost certainly would be possible to take that fixed point, that conformal field theory, embed it in some non-conformal field theory that flows to it in many different ways. But the non-conformal theory has no meaning. The non-conformal parts of it are not part of the S matrix.
Okay, last quick question, Stefan.
There is a stress tensor in the spectrum, so
Yes.
there is a central charge. The question is, what is the central charge? What is it dependent on?
Right. So that turns out to be a surprisingly subtle question. If I interpret your question in the most straightforward way, the answer would be 0. But there is a similar question, which has been answered more completely, about the Katz-Moody level of the U1 current algebra that you get in QED from the soft photon current. And there also the level is 0 for the soft photon current, but there's a second current, which is kind of a magnetic dual, and there's an off-diagonal level, and the second current has a level with itself, which is the cusp anomalous dimension. And so, in some sense, the level there is related to the cusp anomalous dimension. And these two current algebras themselves generate exactly the thing that is known as the soft factor in the QED S matrix. The current algebra of these things is the soft factor in the QED S matrix. And in gravity, there is also some kind of soft S matrix, but it hasn't been studied very well. There are 2 or 3 papers on it. And so there's some kind of interesting story there.
Okay, thanks again.